So you got the assignment solutions, right? Till assignment 4, I think it doesn't provide it, right? Okay, then yeah, let's get started. So yeah, welcome to lecture 7 of this for this course optimization methods. So today in this lecture I will be covering some concepts that has been covered in this last week, that is related to genetic algorithm and all the meta heuristic methods. So these are methods that are being used for solving nonlinear, non-convex optimization problems. So today I will be covering mostly the concepts only and like some solving some problems. So let's get started. So what is the required? There is a requirement of having this meta heuristic optimization methods. So one thing is, like, first of all, we know that we have whatever methods we have used till now, that is the gradient based methods or the simplex method or this kind of methods, these are mostly applicable to like kind of linear problems, or they are applicable to convex problems. So if we have a non-convex, non-linear kind of a problem, in that case we need to have some algorithm that is efficient, that can have and that can provide solution in a better way, or it can provide solution more efficiently. So that is where it comes. There came the rise of this meta heuristic optimization methods. So let us see what are the limitations of the classical optimization methods. So the classical optimization methods are like, one thing is that for the gradient based methods. So the thing is that we sometimes there will might be some points in the search area where we will not be able to calculate the gradient. So there might be a jump, or there might be discontinuity, or there might be a sharp peak. In that case, we won't be able to get the gradient of the function. So our method will fail in that case. So that is one thing. So that is thing. The first thing that comes, that algorithms are not suitable for solving optimization problems with discontinuous functions. So if there is discontinuity, you cannot find a gradient, and in that case, like your method, that is your Newton-Raphson method or your this one bisection method, this will have some problem. The second thing, algorithms are not suitable for solving optimization problems having non-differentiable functions. Again, similar thing. So when you are having in Newton-Raphson, you can see like we are also having the second derivative, that is xi equals to x naught minus f dash x naught by f double dash x naught. So if both the derivatives are not, like one of these two derivatives also not is not defined, in that case we won't be able to calculate we won't be able to do the optimization using Newton-Raphson method. This is also one disadvantage. The algorithms are not suitable for solving discrete optimization problems. Yeah, when there is a discrete optimization problem, in that case we cannot use this differentiation kind of method, and also this interval halving or this bisection or like golden section search. All these methods are based on continuous functions only, so we cannot use those methods for discrete functions. So this is also one disadvantage. And lastly, the algorithms are not suitable for solving integer and mixed integer problems. So this is also similar type to a similar problem like discrete optimization problem. So second thing is, we are always assuming that the problem is a convex function. This is also one thing. For non-convex functions, algorithms may only get a local optimum. Yeah. So we have discussed that when you are taking interval halving or this Newton-Raphson or bisection or even this golden section search, these methods, we always have a starting point. If our starting point is near a local optima, we will get that local optima only. So there is a high chance that will miss the global optima if the function is non-convex. So these are some kind of problems. So you can see. So first one is a convex function, we can find it. But second function we can see it is a non-convex function. So there is a minima as well as a maxima. So third function there is a discontinuity. In that case also we won't be able to get the minimum. This is a function where the function is non-differentiable. At this point the function is non-differentiable. At this point also the function is not differentiable, and this is a discrete function. So in that case also we won't be able to get the derivatives or the differentiation. So these are the limitations that I have to face when we are using classical optimization methods. So this gives rise to the new methods that are called meta-heuristic optimization methods. So these meta-heuristic optimization methods, they are inspired from different algorithms from naturally inspired inspired things. Like one thing is genetic algorithm, which is the most popularly used meta-heuristic optimization method. So the genetic algorithm is based on the process of evolution process in nature. It is survival of the fittest. So how organisms are evolving over centuries, over millenniums, like about 1,000 years, they are evolving with time. So this method is based on that process. Second is a particle storm optimization. So this method is also based on the social behavior of bird flocking or fish schooling. So you can see, like when you see the sky, or you can see the birds are going in a particular shape, or like lot of birds are like they are moving as a group. So when they are moving as a group, they are like not taking any random shapes most of the time. They are taking some different type of shapes based on the wind speed, based on the different situation in that atmosphere. So this is also one particle swarm optimization. This is based on the bird flocking or a fish schooling. Third is a simulated annealing method. This is a process of annealing in metallurgy. It's based on that. Annealing is like when you're in metallurgy, what is it? It is a process used in manufacture of glass. What happens when you have to manufacture glass, we have to melt that glass at very high temperature, and then we have to cool it in a very fast rate. So this heating and cooling of glass is what that gives the toughening of the glass. So this is called annealing process. So some methods, so they have simulated annealing also done to get to solve optimization problems based on this process. Then other methods, there are differential evolution. This is based on biology and evolution of living beings. Then there's firefly algorithm. This is based on flashing nature of fireflies. You can see fireflies will be flashing. They will be only flashing at a continuous rate. It will be blinking at some intervals. So based on that kind of method. And thirdly, invasive weed methods, spreading strategy of weeds. So all these methods are meta-heuristic optimization methods, and it is not very easy to apply these methods for our problems. Just understand that. So to simulate these methods is what we have to understand very deep what's going on in that nature, and it's very difficult to exactly replicate what's going on. It's very complicated process. So we can just simulate with some assumptions and some what you say, not assumptions, and some simplifications. Based after that only we can apply these methods to solve our problems, our simple problems. There are also some other methods like ant colony optimization. You can see ants, they also like make colony, they make ant hills. Ant hills, they're also in some shape. So even if there is a heavy rain or something, like, even if in that case also the ant hills won't be destroyed. They are made in many such a shape that they stay even in they survive in the extreme conditions also most of the time. There are other methods like Antlian optimizer, artificial bee colony algorithm, bat algorithm. There is bats algorithm that based on echolocation behavior of microbats, crow search, and cuckoo search. So these are different kind of algorithms. You can just Google it sometime in a free time and see like what different type of methods are. So this is one thing. Then now, yeah, we will in this course we will be discussing only this one genetic algorithm only, because it is the most widely used method for of meta heuristic optimization, and most widely accepted. So in that, so first thing we have to discuss before going to genetic algorithm, I will be discussing two things that are important in the that is important in this meta heuristic optimization methods. One thing is the random search versus needed search. So when the thing is that in when we have a search space, so there might be a lot of there may not, many optimas, like many maximas and many minimas. So we can have so when you're doing the iteration between the first and the second iteration, there might not be any relation at all. So we are for doing this first iteration and second iteration, we are doing it in a completely independent of the first iteration. So in that case, it is called the random search method. That we are our iterations are not dependent on one another. The second thing is if the information are dependent on one another. That iterations are information is passed from one iteration to second next iteration. In that case, it is called the guided search method. Okay, so this is one thing. Next comes the Darwin's principle of natural selection. So our genetic algorithm is based on a Darwin's principle. That is survival of the fittest. So what does the Darwin's principle state? If there are organisms that reproduce, it is applicable to organisms that reproduce if offspring inherit character of their progenitors. Progenitors means the parents. If they are very built in character and if the environment cannot support all the members of the growing population. So if these conditions are there, in that case, only those members of the population which with less adaptive traits will die out, and those members with more adaptive character will flourish. So these are like some things that are developing with time. So we try to whatever adverse situations we are facing in the climate, in the atmosphere, in the environment, we try to adapt to the changes, and with time we get adapt. We make ourselves adaptable to the new situation. That is how the evolution is taking place over like millions and millions of years. So we will now see what is genetic algorithm. What are the steps for doing this genetic algorithm method? So genetic algorithm are the heuristic search and optimization techniques that mimic the process of natural evolution. So in you can all I have already shown that in natural evolution what is there. So that when we are talking about on organism, the organism will be evolving with time. So genetic algorithm is based on that method. So to apply genetic algorithm, so first we have to see what is the step-by-step procedure. So we will start the algorithm. We will have a initial population. So we'll have suppose we have a lot of sample space is very large. So from that sample space, first we will start select some samples that are fit. So how do we select? We will define a fitness function, and from that fitness function, using the fitness function, we will be selecting some sample space from the initial population, and there should be some diversity in the selected population. It shouldn't be that all the members that have been selected in initial population they are replica of one another. It shouldn't be that case. Else our solutions will there won't be any difference in our solutions. So this is the first condition. Now after getting the initial population, we will do the evaluate the solutions. Like we'll do the optimization method and we'll see the solutions like we are getting to the optima or not from each of the from the population. Then we'll do the termination. Termination is what we'll do. Like we'll set a suppose we'll do for 100 iterations. We set a number of maximum number of iterations. Out of setting the maximum number of iterations, we will give this is a termination criteria that after if the our iterations reach this number, we will terminate our algorithm. So this is a termination criteria. So now before in this termination, like before termination, we will be doing these three processes. These three processes are the main what theme of like of this genetic algorithm method. So first is selection, second is crossover, and third is mutation. So it is a selection is the like suitable suitable samples from the parents population. It's from the initial population. Secondly, crossover between the population. I'll be discussing about crossover and mutation in the later stage, like after some time. And thirdly, there is mutation. We will do the mutation between the solutions, and then we will see how are the like better solutions we are obtaining, and after getting the best solutions, we will be terminating the process. So this is the step-by-step procedure for writing a code. That is like how will the formation of the code be, because genetic you can see genetic algorithm like it's a very complex method, like and it is used to solve only complex problems. So it's like no, you cannot do it with hand. Like solving with hand is useless. So genetic algorithm is done to solve problems via computer code only. So that is we suppose this is a function for genetic algorithm. We'll initialize the population. We'll get the fitness function and get the fitness for each of the sample in the population. And then we will set this criteria. If the fitness function is not equal to termination criteria, we will selection, crossover, mutation, and then finally calculate the fitness function. Okay. The next is uh, the GA operators and parameters determines which solutions to preserve and allowed to reproduce and which ones to die out. So the genetic algorithm will be based on that. That will be preserving the solutions that are good. That is that are good solutions. Will be preserving that, and we will be using it for further iterations. And next we will be eliminating the bad solutions. There are some solutions that won't be giving rise to any optima. So in those solutions we will be neglecting from going into the further iterations. So this is how the select the best and discard the rest. This is the uh, main motive behind this genetic algorithm. So, and after we select the best solution, we will be doing identify and make the multiple copies of the best solution. So we have discussed that to get the solution, we will first for the initial population, we will get a fitness function. So what is a fitness function? A fitness function is used to evaluate the solutions. And suppose like one of the fitness function is like suppose you have to evaluate the cost of like painting a box. Suppose a box is suppose cuboid in shape, we have to find the cost. So will be what will be get a fitness function that is like surface area of the box into the cost per unit surface area. So this is a kind of a fitness function, and then we will be like maximizing or minimizing this fitness function based on a requirement. We need a maxima or a minima. But yeah, in genetic algorithm what we do, it is in nature genetic algorithm is designed to get the maxima only. So even if our fitness function is used for a minimum, as we are getting a minimum for this fitness function, we will convert that to this maxima function, that is f is equal to 1 by 1 plus f. So we will always convert this fitness function to a maximization problem in genetic algorithm. So always remember this, okay. So now we got the fitness function. After getting the fitness function, we will have to uh, do the selection procedure. That is, to select the solutions. So there are four methods that are used for selection. The one thing first is tournament selection, second is roulette wheel, third is proportional selection, and lastly rank selection. So for let's first discuss what is tournament selection. Into what do we do in tournament selection? You can see like in a tournament what is happening, like different teams from like different countries they are playing against each other, and we will select a winner for each round, and then they go to the next round, and this is how a tournament takes place. So similarly this is a procedure here also. So suppose in tournament selection will be several tournaments are being played among a few individuals. The individuals are chosen at random from the population. So we select some individuals randomly from the population. Suppose we select these six individuals, and yeah, one thing remember in tournament selection, we always keep the tournament size fixed. That is number of tournaments between should be fixed. So we'll see. Suppose we select six individuals from like randomly from the population. We will be randomly, and then we'll do the tournament randomly between them. So we have done this. These two, and these two, and then we'll get a winner from each of the tournament, each of the matches. Secondly, now we have to do the matches of these three again, other three, because we know the tournament size is fixed. So again, we will pick some samples randomly, six samples randomly from the India, from the this one from the population, and then again we will do a tournament between them, and we'll get three more outcomes. And how will what we'll do? We'll do the tournament between the two selected as two winners, and finally get a winner. Okay. So what happens will the best solution will have two copies. So the what happens in tournament selection, the solution that is best will have the maximum number of copies. So the maximum number, so if we have the tournament size is three, then the maximum best solution will have a maximum number of three. Three number of best solution will get. The worst solution will have no copy. The solution that is worst will have no copy. So suppose this is one thing. This is a worst solution. So this solution will have no copy at all in the final set. And other solutions which are like not bad, not too good or not too bad, these will have one or two or like that, one copy or maybe two, or even no copy at all. That depends. So we'll have the best solution, and after that we can get the ultimate optimal solution for the problem.
What is this plus 30 and plus 45, sir?
This is a penalty function actually. So these solutions are like not good. So what we are doing, we are adding a penalty to that. So like penalty, adding penalty means this these solutions won't go into the further rounds. That's what we say. Plus 45 means this is like kind of, it's not specific to this problem. Like when we will be solving some problem, then we will get to know. Like maybe in the next week lecture,
Okay.
in that case we will know. It's like this is a penalty. Okay. So we don't keep, and also like we kept here, we kept tournament size equal to 3. So we don't keep very high tournament size also, because we have multiple copies of the, if we have multiple copies of the best solution, in that case also we don't want that kind of situation, because if we have all the solutions best solution, there will be no diversity between the problems, and in that case we won't be getting a global optimum. So our solution will be based on one local region only, localized region only. So we won't be exploring the different parts of the search space. So that is why we will be having a diversity of the problem. So next is roulette wheel and proportional selection. Okay, second selection is roulette wheel and proportional selection. Here what we do. So first, uh, what we do is first the parents are selected based according to their fitness value. So this fitness, suppose we have we mention in the parents as chromosomes. I'll discuss why I'm mentioning as chromosomes, because in genetic, you can see genes, there is something called DNA. In DNA there are chromosomes. These chromosomes have some unique character. So these chromosomes, this is why we're using this term chromosomes here. So for each chromosome, we'll have a fitness value. So this fitness value is based on different fitness function. Based on our problem, nature of problem, we'll have a different fitness function, and based on a fitness function, we'll have a fitness value. High fitness value means is a good solution. So you can see this is the, this solution chromosome 1 has a fitness value of 50, second has 6, like that. So we'll do the next, we'll get a percentage of roulette wheel. So how do we calculate that? We'll do the fitness value divided by the total amount of fitness. That is sum of all the fitness values. So and into 100. So this will give us the percentage of roulette wheel. The roulette wheel is nothing but a pie chart. It is kind of a pie chart. It will show the percentage of the solutions, the percentage of roulette wheel that each of the solution is occupying. So this chromosome 1, there may be lot of chromosome 1s in the this one solution. So this is occupying most of the search space. So this will, if we are start having the solution in this, if we're starting the method in near chromosome 1 or at chromosome 1, will, it is high chance that we will go to the optima in a very fast. So that is why this is a very high fitness value. Now after getting the percentage of roulette wheel, will this will give the percentage. This you can see, this is for, can you visualize, see it? So fitness, yeah, I will. This is that I told already that fitness function is based on the problem method. Suppose I told you, na, if suppose if a fitness is function is like that, that we want the cost of suppose manufacturing a cube. So in that case, what we need? We need, suppose the surface area of the cube is what, cuboid L into B, L cube into B cube, right? So this is the surface area of the cube. Oh no, sorry. So it is like 2 into LH plus 2 into BH plus 2 into LB. This is L, B, and H. This is the total surface area of the cube. We will multiply it by a constant, that is C. This is kind of fitness function that we want to maximize this for the surface area. We want to maximize the cost. Sorry, minimize the cost. So this is a kind of a fitness function. So based on our problem, we will be having a fitness function, and based on that fitness function, we will have a fitness value. So this is a sample how we prepare it. It's not for a specific problem. So our sample it is showing like for a chromosome, for different chromosomes we have this kind of fitness values. For that, how will you prepare a roulette wheel or a proportionate method? That's what it is shown. It is not a series, just a sample. So now we have got a percentage of roulette wheel. So we'll have for like suppose 27% here. This is for the first one. That then again 20% here. This is for the second one, like the 15% here. For the third one, like that, we will have the different percentage in the roulette wheel. Next, we have something called the expected count. That for the for each chromosome based on the fitness, we will have the expected count. How do we get the expected count? Like I think yeah, 26. One second. It is like multiplying this percentage, multiplying this percentage roulette wheel into fitness divided by 100. How we get the expected count? Expected count will be the for each chromosome. What is the expected number of chromosomes that are available for each expected number that is available for each chromosome. So the one that is having the highest fitness value will have the highest expected count, and the one that is has the least fitness value will have the lowest expected count, like 0.19. This is one thing. So now there is the actual count. The actual count it cannot be decimal, so we will be round off this expected count to the nearest integer. So 1.6 will go to the 0.1 will go 0. This is the this is how we got the actual count of a number of chromosomes. It is a number of parent members. So this is often the parents are selected based on the fitness values. The better chromosomes will have more chances to be selected. So the chromosomes with very high fitness value, that is with high expected count, high actual count, will have multiple copies. And so if there are a lot of like a very high number of copies of this very this one best solution, then if we do a crossover also, then also we won't get any new solution. So we always want a diversity in the number of solutions. Suppose in one case this fitness value is suppose very high. Okay, fitness value is for one first chromosome, the fitness value is around 100. For the others it is like 25 6. So what will happen, this value, this chromosome will have multiple number of copies, suppose maybe 6 copies of very high expected count. So in that case, in our final solution we won't be having any diversity of the sample space. So we will be only locally searching the this optima, locally searching the optima, we won't be searching the optima globally. So that is why we always want a diversity in a solution. So just if one solution has very high fitness value, in that case applying this roulette wheel and proportional selection is won't be a very good method to go into the selection procedure, because it will just it will be biased only on the values that only on a chromosome that has very high fitness value. Okay, so how to deal with this situation? To deal with this situation, there is something called the rank selection method. So you can see in this rank selection, what we do, we will assign rank to each of the chromosome. Suppose we have the fitness value like this 86, 20, we got the fitness values. Now we will sort these fitness values, sort this chromosome based on their fitness values. We will sort like descending order of their values 80, 25, 20 like that. Then we will assign a rank 6, 5, 4, 3, 2, 1 based on each of the chromosome. After assigning a rank, what we do in the roulette wheel, we will give the percentage of roulette wheel based on their rank, not on their fitness. Here we did using their fitness only. This percentage of roulette wheel was calculated based on 50 by 187 based on their fitness. But here we will be calculating the percentage of roulette wheel based on their this one based on their rank. So based on the rank, if it, even if that in that case also the highest The chromosome with the highest fitness will have the highest percentage in roulette wheel, but it won't be that high that it will be consuming only 80% or like 90% of the area of the roulette wheel. So it will have some 29, 30 like that kind of percent. This is how we do the rank solution. This is a better method when one solution, one value, one chromosome has very high fitness value. So in order to diversify our solution, we will be using this rank selection method. Okay. So here you can see after that expected actual count and expected count, you can see it is 2, 1, 1, 1 like that. So, but if we go for like in this scenario, if we go for this roulette wheel method, then we'll get the actual count as 6, 2, 1, 1 like 0 like that, 1, 0, 0 something like that. So one is very high, other is very less. Okay. So that is why rank solution is a good method if one chromosome has very high fitness. So this is one parent member. Okay. So these chromosomes are coming from where? So now we'll see how do we define the chromosomes. So like we have, suppose we have a sample space. Okay, we have a population. We are selecting some individual like some values randomly from the search space. After getting the values randomly from the search space, what we will do? We'll convert it to a binary form. You know how to convert values, decimal values to binary and binary to decimal, right? Do you know or not? Like, can you just confirm?
So can you please explain, sir?
What I didn't understand. Can you tell again?
Sir, can you please explain how to decode, sir?
Okay, okay, fine. Okay, so the first thing is encoding. Okay, first thing is encoding. So encoding comes like when you're doing the chromosome. So we have suppose we had decimal value something like 26. Okay, we have to convert it to a binary form. So how do we do? We'll divide it by 2 to 13 to I think there is one thing. Let me check once. Yeah. So this is the procedure to get the this one second. Procedure to get a decoded value of the chromosome. Just one second. Okay, yeah. This is how suppose this number, okay, 26. How do we do? We will divide it by 2. We will write the dividend here 213 and we will write the remainder here 0. Next, we divide again 13 by 2. We will get 6 and remainder 1. Next, we divide it by 3. Divided by 2, we will get 3 and remainder 0. And next, again we will divide it by 2. We will get 1 and remainder 1. So, this is what forms the binary 1 1 0. No, sorry. Oh, it's not 1 1. You have to write from this order, like top to bottom. Okay. 0 1 0 1 1. So this is what forms the binary for 26. Understood? So now, how do you convert from
The remainder will be the last one.
yes, yes, yes.
Okay.
Okay, after 1 you won't be able to divide it by 2 again, right? So we'll be writing the remainder, and the this one, suppose for dividing by 13, the remainder, if we divide, it will get, we get dividend as 6 and the remainder is 1. So we write the remainders here. So and we'll write all the remainders in the from top to bottom. That is how we'll convert from decimal to binary. Okay. Now we have, suppose, this binary form 0 1 0 1 1. How do we convert to decimal? So it's like, for this it's like 2 to the power, we'll multiply this with 2 to the power 0, this with 2 to the power 1, this with 2 to the power 2, this with 2 to the power 3, and this with 2 to the power 4. Okay, understood? So it's like based on a position.
Okay.
So it is like, for the first one it will be 0 into 2 to the power 4 plus 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. So now let us sum. So this is 0, this is 0. 2 to the power 3 is 8 plus, details will do some mistake. It should be 2 to top to bottom or bottom to top. Actually, sorry, it's my bad, my mistake. It's bottom to top. Okay. So this is, it will be this direction, bottom to top always. So it will be 1 1 0 1 0. This is 26. Okay. So now we will see 1 1 0 1 0. I will do. This is 2 into 2 to the power 0 into 2 to the power 1, 2 to the power 2, 3, and 2 to the power 4. So it is 0 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 square plus 1 into 2 cube plus 1 into 2 to the power 4 is equal to 0 plus 2 plus 8 plus 16. This is equal to 26. Okay. Any doubts now? Can did you understand the procedure?
Okay, sir.
Yeah. So it's like going bottom to top. Okay. Bottom to top, you have to write the font in this font, and you'll get the binary value for the decimal value. So this is what. So what we do, like before going to definition of crossover, we should know how to convert the decimal value to a binary value. We're doing it convert it to binary because it is easier. Like when I convert it, all our calculations will be based in computer, right? And computer operations are based on binary only. That is, they convert everything to binary and then do the calculations. So that is why we need to convert. So this is a unique chromosome for 26. This is how we denote as a chromosome, and this is assigned to the number 26. It's like that. Okay. So here, just as in a chromosome, what happens? Each gene controls a particular characteristic of an individual. Similarly, each bit in the string represents a characteristic of the solution. So when you're writing the this binary, suppose 1 1 0 1 0, we'll convert it to bits. So this is the first bit, second bit, third bit, fourth bit, and fifth bit, and this all this convert like accumulates to get a byte. That is one byte. No, no, 1 byte, kilobyte of data, megabyte. You have heard now, obviously, that when you was mentioning storage space and all, 1 byte. 2 byte, 3 bytes, like 1 kilobyte, 3 MB, 3 megabyte, like that. So this all these bytes, the basic unit is the bit, one bit, and for each bit you can see it may be 0 or 1. So this character of this chromosome is is denoted by the value that is here. So if we change from one value to 0 to 1, then the whole character of the string changes, the value will change, and this will change the character of the string. So this is how we denote a chromosome in genetic algorithm method. Okay, this is how we encode the values. Whatever value, decimal values we have from the search space, we'll encode it to binary form in this way. And in some algorithms, what they do, they like also put some part of the string as a hybrid, like some they keep it as binary. This is what the best way. The second way is they keep the values as real also. They can, suppose we have 25 four individual values, 26, 27, something like that. We can keep the decimal values also as a part of a string, and in each bit we can keep decimal values. That is, but that is not a very efficient method for solving. So this will create some problems. So that is why we always try to go with binary only. And there might be some where we want to keep a part of string as real, that is put real values, and a part of string as binary values. But keeping everything as binary is the best way to proceed. So this is the encoded value. Now we have to do the decoding. How do we do the decoding? After encoding, we have suppose two values as 52 and 26. So these two values will be writing it as the whole one string, and we can convert it to binary. This is for 26 and this part is for 52, and then we will write it as one complete string. Okay, so this is the formula that is there, that I have shown only. This xi minimum minus xi max minus xi min for mapping in decimal and binary value. So decoded value, I have shown how to decode from binary to decimal and decimal to binary. That you can do, get a decoded value, and from here you can get the decimal value mapping. Get the mapping if you want. Okay, so this is one thing. This is what goes. Yeah. After that, we will see. So it is called crossover. Crossover is what we will be. Uh, it is used to, crossover is the process where we are creating new solutions from the existing solutions by available in the mating pool by after applying some selection operator. Mating pool is like what? Mating pool? Mating pool is nothing but a collection of some parent solutions. Suppose here we decided, right, we get some good chromosomes. This one is a best solution, then four is a best solution, like that. So we'll take these two solutions into a mating pool because they are good solutions. If we can do some crossover between the genes of these two solutions, then we can get into some maybe better solution. That is what constitutes a mating pool. We will be taking two solutions, and then we'll that take into account, and from that we'll do the crossover. So what we do in crossover? In crossover, we change the gene information. How do we change the gene information? So this is one thing. This is a method. The most popular crossover selects any two solution strings randomly from the mating pool, and some portion of the strings is exchanged between the strings. Suppose we have two values, two strings. Suppose this is for some 56 or something like that. This is for 21, like that. So what we will take these two solutions, we will select the crossover side, and then we will be interchanging this part. Will be this value, this part will go here, and this front top part will come here. This is called crossover between the two solutions. After doing the crossover, what we will get a new string here, and also a new string here because all the values are interchanged, and then we will get a new solution value. Okay, a new solution value, and then we can proceed if you are getting better values in the solution. So this is what crossover is. So crossover is a local search operator. Why local search? Because even after doing crossover, whatever solutions we get here, this new first and second, this will be near to the parent solutions. Suppose this value is 56. Whatever we get here, it might be somewhere around 50, in the range of. So these values will be in the range of 50 to 60. But if for this 21 also, these values, whatever you get in the new child, will be in the range of maybe 15 to 30. It is near the parent solution. Why? What is the reason? Because we are changing the part of the lower part, that is the right hand part of the solution. The right hand part doesn't have that much significance in the solution. Means these values are what? It will be 2 to the power 0, suppose 2 to the power 0 plus 2 to the power 1, 2 to the power 2. We're multiplying with uh, low powers of 2, right? 2 to the power 0, 2 to the power 1, 2 to the power 2, like that. So this, if your string is very long, and suppose this part is suppose someone 2 to the power 15 or something like that, that the final one, very large value. So this changing a part of the smaller part of the string, only changing like too much. Suppose here it is suppose 2 to the 15 something like lakhs, it will be something lakhs, right? 2 lakhs or something like that. Suppose this thing. We're adding we're adding suppose here around even 2000 also, it will be 2 lakhs 200,000. So what? It won't be changing that much. So that is why in crossover we are not changing the too much, changing the too much in the search area. So the new child that we get after crossover, it will be near to the parent solutions. Okay, this is the main concept behind crossover. So sometimes there might be multiple crossover sites also. So like we can select two crossover sites, we may select three crossover sites. It is based on our choice. So here you can see. So these are two values 8 and 10. 8 and 10 are then encoded. 8 and 10 are encoded in this format, right? Just how we saw here, like if 52 and 26 are there, we're encoding like combining the two strings. So 8 and 10 are combined in here, and then there is a second solution 14 and 6. These are encoded in this format. Why? Like why are taking two variables? Suppose we have only two variables, x and y are there. It's a like two variable optimization. So our search space will be 2D, right? In if we are taking two variables x and y, our search space will be 2D, and all our points that we have in the search space will have one x and one y value, right? So that's why we are having two values here. Like say taking a simple example of a 2D optimization problem. If we have n with 9 values, x, y, z, a, b, c, something like 9 values, then we'll have 9 values here, and our chromosome string will be more longer. So just checking for a 2D problem, we have 8 and 10, and we are writing 8 and 10 in this format by heart. You can see. I think yeah, 2 to the power. Yeah, from here. So this part corresponds to 8, and this part corresponds to 10, right? This is how we do the encoding. Because 2 to the power 0 plus 2 to the power 0, 1, all these are 0. The third, I think the fourth term is 1. 1 into 2 to the power 3, this will be 8. Here, 1 into 2 to the power 1 plus 1 into 2 to the power 3, which is there. Okay, this is how we are encoding this for 8 and 10 value here. So second, we have 14 and 6. Again, we are encoding here. Now we select a crossover site based on our choice. And after crossover, we will be changing this part of string. You can see this 1 0 0 0 1 1 0 is coming here, and 0 0 1 0 1 0 is coming here, and we will getting a new pair of solutions. And this new pair, you can see it was 8 and 10. Here you can see 10 and 6. There is not too much variation in the values. Here also it is 14 and 6. It is 12 and 10. So it is somewhere near the search space, near the parent value only. This is what crossover does. Okay, this is how crossover is done to get the new solutions. And also there is one thing called crossover probability. So based on the probability of crossover, we will be giving the probability of crossover also introduced in order to give freedom to an individual solution string to determine whether a solution should go into crossover or not. So like for each of the, we obtain like different solutions here, right? We have like around what 6 solutions here. So each solution will have a crossover probability. So the higher the rank of the solution, the higher is the crossover probability for that solution. The lower the rank of the solution, the lower will be the crossover probability for that solution. So we don't want like very bad solutions to go into crossover, because game, like if you do the mating between a bad individual and a good individual, like it's chance that a offspring will be very bad only. Or okay, so this is about the crossover. Then there is the something called mutation. In mutation, what do we do? Mutation is to diversify the search space. In crossover, we sort of is a local search, like we will get the solutions near the parent solutions. But our if we have our search space like this, we suppose we got our parent solutions and search space like here, and we want some search for solutions here also. What do we do? In that case, we do mutation with so that we get into some different search space and see if there are some good solutions in that area. So in that case, what we do in mutation, we will change the bit. Suppose we have a chromosome here 0011010. So suppose we select this bit, okay, and this bit will change the value from 1 to 0. Changing this value will change the whole value of the string, right? Changing the whole value of the string will also change the solution and will get to some different search space. So this is how what is done in mutation. Like we change the one bit and this will help in searching for to a different explore new search space. The mutation probability is generally kept low because we don't want, like suppose whatever we have done in the crossover, we are already getting some good optima. We want even though we want mutation, we don't want to too much diversify. It will just too much diversify our iteration, because this will create unnecessary unnecessary this one stress on the procedure in the this one code, because if we're searching too many areas in the search space and some areas, most of the areas will won't have any optima, so we should be having only searching for some regions where there might be optima. Going to see for only some regions where the optima might be available, so we shouldn't go into too many regions where there is a where the optima will not be available also. So that is how we proceed. Just 1 second, okay, I have to take a call. Just 1 second. हाँ हेलो. हाँ बोल क्या हुआ. अरे क्लास में हूँ यार, पीरियड क्लास से कर. Yeah, sorry for the interruption. So this is what we do in mutation. We want to go into the new search space, and we don't want to go explore too many search spaces because it will just make our solution procedure lengthy and put unnecessary stress in our code. That is, it will unnecessary stress in our computer code, and our computer, like, it will take a lot of time to get the solution. Okay. So the mutation probability is always kept very quite low, so that we explore some parts of the search space, but not all the parts of the search space. Okay, so these were the concepts. So any doubts till now? If you have, you can ask. Else we'll just go through some small like conceptual problems. Just let me know if any questions, any doubts. Okay, then if there are no doubts, I will just proceed to solve. Like it's not solve. This is just some small questions. Something. Get some question. Okay, genetic algorithms involve which of the following phenomena? Yeah, it involves mutation, it involves crossover, it involves selection. So all of the above. If the parent solutions are 1110111110 and the crossover site is 5, which indicates one of the new offsprings. Okay, so 111011, and other is 101010. Crossover site is 5, 1 2 3 4 5. So this is the, we take the crossover site from the left. Okay, so this is the crossover site. So we'll get the new offspring, new solutions. It's 1 1 1 0 1 0 1 1 0 1 0 1 1 1. So 1 1 1 0 1 0 1. So 1 1 1 0 1 0 1 is a new solution. Other is 1 0 1 0. So 1 0 1 0 1 1 1. This is not it. So one of the new offsprings is 1 1 1 0 1 0 1. Okay. Simple crossover method. Just remember you have to take the crossover side. Yes.
We can take from any top or bottom. We can interchange, sir. This crossover.
No, no, crossover side you take from left only. Okay.
No, not. I'm asking first. Whether we are
Like what? Can you? I didn't understand.
suppose this I can take bottom row is 10. First two rows 10 is there bottom.
Yeah.
So I can take as 10 and top of 5 rows 10, 10, triple 11. I can both values I can take for crossover.
10 means you are saying this thing you are changing
Ah,
here.
yes.
No, 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 no.
Okay.
I already told you that in crossover, what we do always take the left part. That is the part that has lower significance
Okay.
because it is a local search method.
Okay.
I told you because these parts suppose what multiplied by lower powers of 2, right? So if you're multiplying the lower powers of 2, it will be getting the new crossover solution that we get. It will be somewhere near the this one, the original
Okay.
parent solution.
Okay. Okay.
If we
Okay.
change this thing, then there may be a large change in the value. So in that case, we won't be searching. It's a local search. We won't be searching locally. Our search region is completely shift. So it won't be giving any efficient solutions, or it will take too much time to convert. Our solutions won't be converging properly. Okay. So yeah, when we are doing crossover, we always change that part that is less significant. In less significant in the sense like it is multiplied by lower powers of 2 so that we get the solution new offsprings near the parent offsprings. That is parent solutions. Okay, just keep that in mind. Next, the genetic algorithms for the optimization is most likely to succeed. A small population of fitness similar individuals, a large population of fitness similar individuals, a small diverse population of fit individuals, as a large diverse population of fit individuals. Yeah. So genetic algorithm is it can be used for large population and also a diverse population. The population should be diverse. In that case, only our method will be good because if a population is not diverse, the crossover won't be giving any new good offsprings. Next, genotype in natural evolution resembles which of the terminology genetic algorithm. So genotype in natural evolution resembles which terminology in our algorithm. Parameter set, a decoded structure, no. Feature or character, no. Structure or coded string, yes. Why coded string? Our suppose we have coded the string in such a form, so this represents one chromosome, and each chromosome is a genotype. Okay, understood that? I discussed that in the previous slides. Gene in natural evolution resembles with whichever terminology in genetic algorithm. Gene, like each gene is like you have different genes, right? In your each person has a different character. Like he has good genes means like his genes are like very good, like in he might be very good athlete, so his genes are like more like more properly aligned to that is in making him a better athlete. And some people have my genes like who are very intelligent or very talented people, like very like Albert Einstein, Newton, or this kind of people. So their genes are like very what smart, very different, so because of that they are very smart. So this genes signifies the feature or character of a individual or a character of a street. So the gene in natural evolution resembles feature terminology, it resembles the feature or character of the genetic of the uh, string or chromosome in genetic algorithm. The fitness function in genetic algorithm is a function to measure the fitness of a candidate solution. Yes, this is a true fact. Like we get the solution, we have a candidate, and we want to find the fitness of that candidate. This is how a fitness function is used. Next, genetic algorithms are what? Okay, there are multiple options. A class of algorithms that try and build solutions by introducing evolution and selection of the best in a population of candidate solutions. Yes, we have evolving solutions by using crossover and mutations, and also we are selecting the best solutions by using this tournament selection or roulette wheel or rank selection. So it genetic algorithms it try and build solutions by introducing evolution and selection of best in a population of candidate solutions. This is true. Second, a method based on the theory of natural selection and evolutionary biology for solving optimization problems. Yes, it is based on biological method. Technique for genetically modifying ants to do no. This is not for that. There is something called ant colony or ant colony optimization, something like that. Then the third, for last is a heuristic search method used for artificial intelligence and computing. Yeah, genetic algorithm is very extremely widely used in artificial intelligence (AI). You know, robots and also they need to be coded or they need to be coded so that they can resemble some features of humans. So how do you do? They do use the genetic algorithms or this kind of optimization method so that they replicate to some problems in like the humans do. So this is how robots are the algorithm of robots are made. So one, two, and four options are correct. Next question. The genetic algorithm is suitable for parallel computing as it has operators like reproduction, crossover, and mutation. Yeah, this is okay. Fine. It is a population-based approach. It does not require gradient information or objective function. It is a robust optimization tool. So it is robust and all, but this is a population-based approach. So when we have population, we can divide the population into different parts of population, right? So that is why in that case we can parallel computing is what we allot. Suppose your CPU, okay, this is a CPU. In a CPU, different cores, core 1, core 2, core 3. You can maybe heard when you buy a PC, this says 16 core CPU or 24 core CPU, 32 core CPU. So suppose there are 4 cores. So we'll be allotting some part of population in each of the core, like some 20%, 25%, 25%, 30%. So that for each of the population part, it will be doing the solution in the different cores, and this will help in obtaining the solution in a more efficient and more quickly. Okay. So because of population based approach, it is suitable for parallel computing. So in parallel computing, what we do, for each of the cores, we do the computations parallelly. It's not like we do for one core, apply all the population to one core. It's not like that. We do the calculation in each of the cores in the CPU parallelly. This is what parallel computing is. Now, ninth, the genetic algorithm is a powerful tool for both local and global searches simultaneously. Simultaneously, yeah, it is true. A powerful tool for global search. Yes. So the thing is that we are not searching the local and global simultaneously. We are doing one by one. So it is a powerful tool for global search. And why? Global search, because you are using this crossover and mutation. This will help us in searching different parts of search space to get into better like global optimum solutions. Next, the tenth, let the population of a chromosome in a genetic algorithm be represented in terms of binary number. The strength of the fitness of a chromosome in the decimal is given by this function f of x by sigma f of x, where f of x equal to x square. Okay, so x is the decoded value of the string. The population is given by p, where the strength of the fitness of chromosome 11000. So first, let us get the value of decoded value of each of the chromosomes. 01101, 11000, 01. So this will be 2 to the power 0. This is 2 to the power 2. This is 2 to the power 3. Right? Corresponding to 1 only, I am writing the coefficient of 2, because for others will be multiplied by 0. So 2 to the power 0 plus 2 to the power 2 plus 2 to the power 3. 8 plus 4 plus 1. 13, right? So here 0, 1, 2, 2 to the power 3 and 2 to the power 4. 16 plus 8 equal to 24. 0, 1, 2, 3. So 2 to the power 3 is equals to 8, and for this 0, 1, 2, 3, 2 to the power 4, 2 to the power 1, 2 to the power 0. 16 plus 2 plus 1, 19. Okay, we got these values. Now we need to get the this one, the strength of fitness. Strength of fitness is what? This fx is given. Fx is the fitness function. For 13 it is 13 squares are 169. Next for 24, this 24 square. Next is 8. 8 square is 64. And for 19 it is 19 square is 381. 381 or 361? 361, right? 576. So we need for the second one, right? For 11000 is 24. So what do we get? So it is approximately 0.49. 0.49 means it is approximately 0.5. Okay. I hope this is clear how decoding is done and how this fx is square, fx is x square. That's why we are calculating the 30 like square of the decoded values. Okay. Let's see the next question. Now, crossover is a convergence in nature and mutation is divergence in nature. Yes, that's true. Why? Because in crossover we are looking for local search in the near the search area, that is a parent solution. In the mutation we are totally changing the search area. We are exploring new search areas. So we are diversifying our solution. So mutation is divergence in nature and crossover is convergence in nature. For steady convergence, a high value of crossover probability and a low value of mutation probability is to be used. Yes, that is true. I already discussed the reason why. In crossover, we want a high amount of crossover because we want to see more amount of optimum, like near what the parent, like strong parent solutions, and low mutation because we don't want to see all of the search space, because if we give a high mutation probability it will be searching places where there is no optima at all also, so it will just make our computation inefficient. So that is why we will be giving low mutation probability and high crossover probability, so that our solution will be converging and will be converging the solution in a very sooner way. The primary search operators in genetic algorithms are crossover and mutation, crossover and selection, selection and mutation, selection and elitism. It is crossover and mutation. The mutation operator in genetic algorithm requires one solution, two solutions, three solutions, four solutions. The mutation operator requires only one solution. Okay, because we are changing the bit, that is from 0 to 1 or 1 to 0 for only one solution. We are not changing you are not taking two solutions into account. For crossover, we need two solutions. For crossover, we are interchanging the this one that bits from a crossover side. So for crossover, we need two solutions. For mutation, we need only one solution. Next, suppose you are applying a tournament selection and using a tournament size of 2. The worst solution in the population will have, we already discussed that worst solution will have a 0 copy. There won't be any copy of the worst solution in the final solution. Second, suppose you're applying a tournament selection and use a tournament size of 3, then the best solution in the population pool will have, a best solution will have 3 copies. Because the maximum number of the tournament size is there, so the maximum number of best solution is the number of it is size of the tournament. It can have less than 2 or 3 also, but it will have always 3. So 3 copies. Suppose a solution in a population is 1110111, a random number generated to determine the mutated bit of a string, and a fourth bit is selected to mutate the solution. Solution after mutation is is 1110111. So the fourth bit. So see, this fourth bit is always calculated from the left. Okay, 1, 2, 3, 4. So this is mutated means this is converted to 1. So final solution will be what? 1111111. The decoded value of the binary string 1110111 is, okay. You can just do again like 1110. So it is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 4, 2 to the power 5, and 2 to the power 6. 2 to the power 6 plus 2 to the power 5, 64 plus 32. So how much it will be? I think it will be 119. I think, yeah. So these were like today's questions. Any doubts? Anything you have to ask or previous assignment? Anything? Just you can ask me now, because I think these are previous for whatever concept I have covered or what is concepts are as covered in this week. I did whatever problems are required to understand that. It will be more clear when we will be like in the next week when we will be doing some problems, and then maybe in the code we'll get a code to get a solution. Any doubts you can ask me. Not require, like, where did you get? I didn't understand the question properly. Can you just explain?
Hello.
Yeah.
Sir, the gradient algorithms, what parameters require, sir?
No,
Is
in
it
grade.
is it evaluation of the Asian matrix or starting point to starting the iteration?
Yeah, yeah. These things are in genetic algorithm. You don't need this here.
Asian matrix.
We don't need anything like that. That is the advantage of genetic algorithm, right? This Hessian matrix, you have to suppose there is a discontinuity in the function, or there is some gap in the function, or there is some
Mm.
point in the function where the function is not differentiable. In that case, we won't be able to calculate the Hessian matrix, right? Or all
Oh,
values will be, we won't be able to calculate that. So we won't be able to use our that Lagrangian method or this classical optimization method in that case. So that is
oh,
where this genetic algorithm comes into account. It doesn't have anything like that. We don't need not calculate any derivative. We need not see in there if there is continuity in the function. We just have one thing, that is a fitness value, and fitness function we have to form based on our requirement. And the fitness function is the what? It is the optimization function that we have to optimize, right? So the fitness function is the optimization function. Okay.
Okay, sir. Only
After
fitness function is required, remaining are not necessary.
yes, fitness function is
Okay,
necessary. After that, we'll be doing the procedure based on this crossover mutation and this kind of thing.
okay, sir.
Okay. Yeah. Anything else? Okay, then if there are no doubts, we will see in next class. And yeah, if there are any doubts, you can ask in next class also. Okay. Thank you. Thank you for attending. Have a good evening.